Risk is something that we encounter and deal with all the time. When you buy financial instruments, when you cross the street, or when you use third-party software in your application. All these are associated with a risk. Some are low risk and some are higher. In this fifth part of cybersecurity terminology, we will look at the concept of risk. You will often encounter erroneous or sloppy usage of the word, so let us take a proper look at what it is. We will here focus on risk in the context of information and cybersecurity, though the discussion will often apply in a more general setting. In the Internet Security Glossary given in RFC 4949, risk is defined as an expectation of loss expressed as the probability that a particular threat will exploit a particular vulnerability with a particular harmful result. The key term here is the expectation of loss. This expectation is related both to threats, vulnerabilities, and the possible impact. In general, the threat and the vulnerability parts are combined and considered as the likelihood of an event. The expectation of loss can then mathematically be written as the likelihood times the impact. This multiplication does not have to be a real multiplication, but it could be, depending on how you want to consider and compute the risk. The impact is here seen as the actual loss if an event occurs. By multiplying this with the probability of the event occurring, we will get the expected loss. We often distinguish between three main approaches to determining risk. These are qualitative, quantitative, or semi-quantitative. The main difference here is how you go about to measure the risk and how you express the risk. In a qualitative approach, you start off with a set of levels, for example low, medium, and high. Then both the likelihood and the impact is assigned one of the levels depending on the probability of the event and the impact if the event occurs. Finally, the risk is a predefined combination of the two severity levels. In this example, a low likelihood of occurrence but with a high impact will result in a medium risk. There is of course high flexibility on how to define the levels and how they should be combined to the resulting risk. When a qualitative risk assessment has been conducted, a reasonable strategy would be to start mitigating the critical and high risks by implementing appropriate security controls. The rest can be left without security controls for the time being. When risks have been mitigated, a new assessment taking the security controls into account can be conducted. The quantitative approach is more directly related to the mathematical definition of the risk, equaling the product of the likelihood and the impact. The likelihood is given by the probability of occurrence over a certain time period. The time period is typically 1 year. So using estimates, historical data and statistics from similar events, we could estimate that the probability that an event occurs during 1 year is, say, 20%. So we expect that it happens about once every 5 years. Looking at the event, it could result in, for example, the loss of data, the leakage of sensitive data, or server downtime. Depending on the impact, the organization will have some cost for restoring data, loss of sales due to bad reputation, or a service being unavailable, or perhaps fines for not being compliant with regulations. As an example, let's say that we expect a monetary loss of $300,000. Then the risk is $60,000, 20% times $300,000. This is what we expect to lose on a yearly basis due to the identified threat. Now, a quantitative approach that gives the risk in a monetary value allows us to make informed decisions regarding the purchase of countermeasures and the implementation of security controls. In this example, assume that we are considering purchasing a tool that will lower the likelihood of the threat being realized. The tool will cost us $10,000 per year, and we estimate that it will reduce the likelihood to 5%. The new risk based on this likelihood is $15,000. This gives us a saving of $35,000 per year. $45,000 is the risk reduction minus $10,000 for the tool. If our likelihood and impact estimates are correct, it seems to make sense to buy this new tool. To separate the risk before and after countermeasures are in place, the risk with no countermeasures is called the inherent risk, while the risk that remains when a security control are accounted for is called the residual risk. Of course, we could add more countermeasures that lowers the likelihood even more, or we can, for example, get an insurance, have data backups, get better locks, or whatever is appropriate for lowering the impact. This will also lower the risk, and we should make sure that the cost of the security control is less than the reduction in the risk. Otherwise, it would be better to just accept the risk. Let us compare the qualitative and quantitative approaches. Looking at the qualitative approach, it has its advantages in that it can be done without lots of data. It is an expert's opinion, and as such, a qualitative risk can be determined rather easily and quickly and can result in a short list of risks that need immediate attention. At the same time, it does introduce ambiguities since it is not based on real evidence and data. What is a high risk to some could be a medium or even low risk to others. The quantitative approach is much more formal and rigorous and is based on real data. It gives a more detailed ranking of risks and is potentially much more accurate than the qualitative approach. As such, it gives a better basis for business decisions and technical decisions. On the other hand, it can be quite slow since it requires collection of data. When making decisions based on the risk levels, there is also an implicit assumption that the estimates made are correct. A semi-quantitative approach provides a middle ground between the qualitative and the quantitative approaches, hoping to benefit from the respective features. It aims to be faster and less complex than the quantitative approach. Interaction between threats and multiple impacts can require advanced mathematical models. This is avoided in the semi-quantitative approach. At the same time, it should be more consistent than the qualitative approach. To illustrate a semi-quantitative approach, we use the OWASP risk rating methodology as an example. The goal, as always, is to determine the likelihood and the impact. OWASP proposes to do this by dividing them into clearly defined subcategories. Starting with the likelihood, this would depend on two factors: the threat agent or the adversary, and the vulnerabilities that allow the threat to be realized. The threat agent factors are, in turn, how skilled the threat agents are assumed to be, how motivated they are, for example, how high is the reward for realizing the threat. The opportunity is defined by how many resources are required to carry out the attack, and the size, how many potential threat agents there are. For example, can it be done by anyone with internet access, or do you need to be authenticated or have access to the development environment? The vulnerability factors are how easy it is to find the vulnerability that has to be exploited for the attack to succeed, how easy it is to exploit the vulnerability, how well known the vulnerability is, and how likely it is that the exploitation of the vulnerability is detected by, for example, the intrusion detection system or system logs. For transparency and repeatability, for each of the factors, it should be clearly defined what is required to get a certain score. OWASP provides examples to start out with, but they can be tailored to the needs of each organization. Without going into details, assume that each factor can get a score between 0 and 9. We assign each factor a score, and the likelihood is given by the mean of these scores. In some literature, you may encounter an alternative definition of risk, namely that it is given by the product of threat, vulnerability, and impact. Comparing the two definitions, we see that they are equivalent in the sense that the likelihood has just been split into the product of the threat and the vulnerability. This split is also visible in the OWASP risk rating methodology. Again, note that the multiplication here does not have to be a real mathematical multiplication. You could see it as a way to show that the risk increases when the factors increase. Then exactly how to combine them will be up to the model. Similarly for the impact, this is divided into factors affecting technology and factors affecting the business. The technical impact is in turn divided into loss of confidentiality, integrity, availability, and also accountability, that is, to which extent can we trace the attack to an individual. The impact on the technology will extend to impact on the business. Understanding the business and how it is impacted is vital to justify the investments that have to be made on countermeasures. The business factors consist of how much financial damage will result from an attack, the damage to the business's reputation in case of an attack, to which extent compliance is violated, and how much personally identifiable information that could be exposed in an attack. The business factors that are important to consider are often unique to each business, and each organization needs to figure out if other factors are needed or if some could be excluded from the list. Again, each factor is given a score based on its severity, and we compute the mean. Separating technical and business impact allows us to give a score for each. In this example, we can, for example, see that the business impact is much higher than the technical impact. This is a result of the threat having a huge impact on confidentiality and basically no impact on integrity and availability. However, this leakage of sensitive information has a huge impact on the business. From here, we could use the numbers as is and combine them with the likelihood to compute the overall risk by taking the mean. OWASP suggests to translate the likelihood and impact scores to low, medium, and high depending on the score. 0 to 3 is low, 3 to 6 is medium, and 6 to 9 is high. So the likelihood is medium, the technical impact is medium, and the business impact is high. Now, using the same table as we had before in the qualitative approach, we can say that from a technical perspective, we have a medium risk. But from a business perspective, the risk is high. Since in the end it is the business that needs to be protected, the risk should probably be considered high. If we instead would have combined the technical and business impacts using the mean score, we would have reached the score 5.75, which in turn would translate to medium. With medium likelihood and medium impact, the overall risk would be medium and the high impact to the business would have been missed. Exactly how to do this, both with regards to which individual factors should be used, how they are scored, and how to combine this data to an overall risk, is not only possible to tweak, but it is advisable to tweak it depending on the needs of the organization. In any case, it is clear that such an approach provides some of the accuracy, transparency, and granularity of the quantitative approach, while also being reasonably efficient to perform, similar to the qualitative approach. Still, it should be noted that the distinction between the three approaches is not an exact science. Some would argue that using the matrix to combine likelihood and impact would always fall under semi-quantitative approaches, regardless of how the underlying data is used. This concludes this short overview course on cybersecurity terminology. There are still many terms that have not been covered, but by understanding the terms that we have covered, you will be better prepared to distinguish different technical controls, countermeasures, and cybersecurity tools and the information they provide to help you keep your systems and applications secure.